Okay, so I'm going to show you the implementation of the preconditioned conjugate gradient. Here the x naught is just going to be, we're not going to make the user pass in x naught, and then we're going to give a precondition. We're going to call it none for now. Okay, so there's a couple of things that we have to do to set stuff up. I'm just going to copy a lot of code. So like here, I'm going to copy this. We're going to have this. Okay, that's running okay. Now this is the algorithm here. Now m is the preconditioner, so like m inverse, p is equal to m inverse. So we're gonna do this like we're gonna set this up like we did before. So if you come to look at the algorithm here, we have z naught is equal to m inverse r naught. Well, this m inverse is going to be that linear operator p. So that's the sort of thing that we're going to have happening here. But just like with conjugate gradient, we need to kind of set. This is the conjugate gradient algorithm. We need to do this this setup here first. So we're going to let x naught is just going to be the 0 vector. And then we're going to look at this stuff right here. So we're going to have to make some changes here due to the preconditioner. So let me do this one other thing. So with the way that the preconditioned Jacobian algorithm is implemented, we're not. I mean, in principle we are, but in the code it's not like we're just applying the conjugate gradient algorithm to a preconditioned system, because the preconditioned system, if we just do a naive preconditioned system, that system is not going to be positive definite. It's not going to be symmetric or positive definite. And so what we do instead is sort of take the Cholesky decomposition for our preconditioner, which is what we have here. So the preconditioner m needs to be symmetric positive definite as well, so that it has a Cholesky decomposition. Otherwise, this doesn't work. Now, we're not going to use the Cholesky decomposition in the algorithm. We're just going to use it to derive the algorithm. And so what we're going to do is we're going to let x equals p inverse transpose y, and then we're going to precondition on the left with p inverse. And so this is what we're going to get. Okay, and so what we do then to derive the preconditioned conjugate gradient algorithm is we just apply conjugate gradient to this system, namely, this system right here. If we apply it and then sort of make some changes like p hat j is equal to p inverse transpose pj and similar such replacements, we eventually get an algorithm like this, or this would be like the update of the algorithm. I'll let you go through the derivation. The issue here is that the thing that we're calling zj hat is the residual, so it should be called rj hat, which means this thing we're calling rj hat should be zj hat. So we should reverse both of those. If we do that and then get rid of the hats, because we don't need the hats anymore, the hats were just for the derivation, this is the system that we get right here. Okay, and so now we can now solve this system of equations. And again, I think I said a minute ago that I was going to set this up like we did for Big Stab, where P is going to be a linear operator, and that's exactly right. I'm going to set this up like we did for Big Stab. So now we're going to begin the loop of the algorithm. So we're going to begin with R naught, which we've already computed. But now notice Z naught is equal to M inverse times R naught. But M inverse is P, so it's going to be P at R naught. This is the whole linear operator thing that we're dealing with. And then P0 is going to be equal to Z naught, and we're going to set J is equal to 0. And now we can look at our main loop here. So while J is less than max iter, we're going to do the following. Okay, so this right here, this is not the preconditioned A. That's just the A. So we're not going to have to do we're not going to have to do what we did before for Big Stab and compute like P times A. That A is just A. The way the preconditioner is felt is down there. Okay, So I've noticed that I'm going to be computing AP a couple of times. So I'm going to say AP is equal to AP. And I think that's the only vector computation that I'm doing here. The other one is going to involve M. So that's going to be AP. Oh, but I need to set P is equal to P naught. I don't think this is gonna, I think this is what I needed to do. Okay, sorry. P is equal to Z naught. There's sort of a typo here. Well, not really a typo because we're using J's here. Anyways, all right. There was just an error in the way that I had coded it, a slight error. So A is going to be equal to Z, ZR divided by APP. Okay, and then X is going to be equal to X plus A times P. A times P, like this. Whoops. A times P. Then R is going to be equal, oops, R is equal to R minus A times AP. Okay, now we need Z. Z is going to be equal to P times R. And now beta, I'm not going to use B because that's the right-hand side. So beta is going to be equal to, okay, so I'm going to have to save R for a second. So hold on, Z, the new Z and the new R divided by, I'm going to, you know what, I'm going to call this ZR. ZR, because it's the old Z and the old R. So I'm going to say ZR is equal to ZR. Okay, then I'm going to update Z and R, so I'm going to divide by ZR here. Okay. And then the new P is going to be equal to Z plus beta times P. Okay. Wow. Now R here, R is the residual. Okay, so we don't, I mean, R is the exact residual, so we don't have to do any adjusting of the residual here. So R norm is going to be equal to np dot linalg dot norm. If R norm is less than target, if R norm is less than target, we're going to do this. Okay, so run this on preconditioned conjugate gradient. This is way too many iterations. It doesn't really matter though. P equals P. And let's just see what happens here. Actually, let's see what happens. So when I run preconditioned conjugate gradient and I don't tell it what I want the preconditioner to be, it should just default to the identity matrix. So let's see what we get here. All right. So I didn't initialize Z. Oh, this needs to be Z here, not Z not. That's going to be Z2, okay. That needs to be, oh yeah, R is equal to R not. Man. Well, this is embarrassing. X is equal to X naught. Okay, there we go. And we get basically the same exact thing because, oh, I didn't update my J's for PCG. Here we go. And we should get the same exact thing for PCG and CG because in exact arithmetic, the unconditioned PCG is just CG. Okay, so now let me precondition. Okay, so now we can come down here to test it. Now, okay, here's the thing that is true. We can't use a lower triangular solver here or preconditioner here. Why? Well, because for a preconditioned for conjugate for a, to precondition conjugate gradient, remember the preconditioner needs to be symmetric, positive, definite. So what we're going to do here instead is we're going to say the preconditioner then is just going to be the 1 over the diagonal matrix. Okay, so the preconditioner is just going to be 1 over the diagonal matrix. We don't need to do this linear operator stuff. We can just say P is going to be equal to SPS dot diags 1.0 divided by a 4 dot diagonal format CSR. Okay, that should work here. I ran it before. The reason it has that bad numbers there is because I ran it before and I had P still with the lower triangular matrix. Now, when we run this, we should get something better. Now, it's a little, I get this a little disappointing that it took long, that the preconditioned matrix took longer to run here. Not exactly sure why that is. On the other hand, if we come up here, so this matrix, this is a poorly conditioned matrix, and so it's taking an extraordinarily long amount of time to run. This is very surprising that it takes that long to run. But if I come up here and I precondition, so let's see how the preconditioned gradient is going to work on this one. This needs to be A3, and then we're going to do preconditioned conjugate gradient, and we're going to do this with the 3's. All right. Oh, because I still have the X4 there. Okay. Okay, so oh, I see, because I didn't have enough iterations. So let me increase the number of iterations here. Still not where we need to be. Increase the number of iterations again. Okay, so now we can see that the precondition. So, like I said, what is the matrix that we're applying it to here? This matrix A3 is not positive symmetric. Is not symmetric positive definite. This matrix is, because we're doing A3 times its transpose. If we just do the normal conjugate gradient on it, we get this, we get horrible convergence. I mean, 30,000 iterations is very slow. But notice if we just do this very simple preconditioning by just dividing by the diagonal, we get a much better convergence rate here. So this is 30,000, this is 1,000, so we're doing 30 times fewer iterations. So it shows this, it gives an indication of why the preconditioning works well. So here, the preconditioning, it's not so much that it made things worse, because notice we have a better error here. So I guess the preconditioning here was better because at least it converged. Whereas maybe if I make this go to 10 here, maybe that'll be a fairer test. Yeah, now they're both taking 43 iterations, and we get slightly better errors here. I wonder what happens if we do 15 here and 15. Whoops. Oh, both. That's interesting to me. Okay. Well, anyways, that just shows that this is a very well-behaved matrix, whereas this one isn't. Okay, well, anyways, that is the preconditioned conjugate gradient algorithm.